Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Okay, well, we've completed all 5 essential topics or skills for the mini course Preparing for Success in Organic Chemistry. But before we close this out, I did want to add one topic, and that would be functional groups, and say a little bit about that. I've mentioned functional groups from time to time. Certainly when we've seen ketones and aldehydes and esters and amides, alkenes, alkynes, these are functional groups. I think you know that. But what I want to do is give you a sort of an org chart, which I think will be real helpful to you when you actually start your course. So that's the purpose of this last video lesson in the series. So let's talk about functional groups in organic chemistry. This will not be an exhaustive compilation of all possible functional groups. There are probably over 200. We're certainly not going to be looking at that, but I do want to give you the common ones, tell you a bit about them, and again, give you a sort of a categorization scheme that I think is going to help you when you begin to actually study these in more detail. Well, first of all, what is a functional group? Here's my working definition. I'll read it. A set of bonded atoms that are part of the overall structure of a molecule and which behave in a predictable manner regardless of the rest of the molecular structure. All right, so what does this mean exactly? Take a look at these structures on this slide. Let's start on the left-hand side with the left-hand upper molecule. Very simple molecule, right? N-propyl alcohol, N-propanol. And so if you understand the behavior properties, reactivity of N-propyl alcohol, that means that you essentially also understand the behavior properties and reactivity of more complex alcohols like the one directly below it. This is the idea behind functional groups, that there are subsets of atoms and bonds in an overall molecular structure that act more or less independent of the rest of the structure and have predictable behavior and reactivity. All right, let's look at the middle set of compounds. Right, you wouldn't normally say that the upper simple compound, which is methyl acetate, has much in common with the more complex 7-membered cyclic ester, which is called a lactone, right below it. But in fact, if you know the behavior and reactivity and properties of a simple ester like methyl acetate, then that means that you also pretty much know the behavior, properties, and reactivity of a much more complicated structure like the one below. Let's look at one more example. On the right-hand side of the slide, if you know how simple alcohols and simple esters behave, right, those two simple molecules above, then that means that you can make predictions about the behavior, properties, and reactivity of a molecule where both functional groups are contained in the same molecule. This is the idea. Now, let me just say this let me say one more thing about this. There can be, certainly in the last case, right, is a di or really trifunctional compound. You have an alcohol, you have an ester, you have an aromatic ring, a benzene ring, really 3 functional groups. And the way I've just discussed it, they act independently. There are certainly many examples where polyfunctional compounds, molecules with more than one functional group, act in concert. And they do things and behave in a way that the individual functional groups do not or would not. This happens all the time. This is especially true of what are called conjugated and non-conjugated systems. But I just wanted to give you a basic idea of the concept of the functional group in organic chemistry. All right, so let's start with this org chart. At the very top, you have all functional groups in organic chemistry. But again, like I said, I'm not going to be burdening you with 200 functional groups. I'll give you the common ones, the most important ones. So the first split that you see in this org chart, right, going down to the second tier, is the split between hydrocarbons, right, and non-hydrocarbons, right? In fact, I should have another tier there. There's just no room for it. I should have another tier that shows, it's either a hydrocarbon or it's a non-hydrocarbon. But this should do fine. Hydrocarbons, of course, are compounds that are comprised only of carbon and hydrogen. There are non-aromatic hydrocarbons, which basically don't contain a benzene ring. Let's just leave it at that for now. And there are aromatic hydrocarbons that do contain a benzene ring, and that's what's shown as an example here. You can see some compounds for aromatic hydrocarbons. The right-hand box that says ONSPB. So if a molecule is not a hydrocarbon, that means it contains one or more heteroatoms. And a heteroatom is any atom or element that is not carbon or hydrogen. It might be oxygen, it might be nitrogen, it might be sulfur, it might be phosphorus, boron. X is halogen, M is metal, and of course there are other possibilities as well. These are the most common ones. Okay, now going back to non-aromatic hydrocarbons. Okay, you have 4 subcategories under that box. You have what are called fully saturated alkanes, which are hydrocarbons that have no double or triple bonds and no rings. No double or triple bonds and no rings, and they follow the formula CnH2n plus 2, where N is equal to 1, 2, 3, 4. Right? 1 methane, 2 ethane, 3 propane, 4 butane, 5 pentane, so on and so forth. Then you have your cycloalkanes, which have no double or triple bonds, but have 1 ring. And those have the general formula CnH2n. Then you have your alkenes, right, which of course is a carbon-carbon double bond with the formulas that you see there. And you have your alkynes, which is your carbon-carbon triple bond. Those all fall under the category non-aromatic hydrocarbons. Aromatic hydrocarbons, we already said, contain 1 or more benzene rings. All right, now going below this, we have your oxygen-containing functional groups, and there are 3 major functional groups that contain oxygen. And I probably should also have a line right from that upper box that has the heteroatoms to a subset, which is oxygen only or oxygen containing. You have your alcohols, which you see again indicated in a general structure. That's a sp3 carbon bonded to a hydroxyl group. Again, R's are either hydrogens or alkyl groups in this system. You have your ethers, where the oxygen is bonded to 2 carbons or 2 alkyl groups, and then you have your carbonyl compounds. The carbonyl family is the family of compounds that contain carbon-oxygen double bonds. The carbon-oxygen double bond is the carbonyl functional group. And I show one more thing here. I show that a very important subcategory of ethers is the cyclic 3-membered case, which are called epoxides, and these occur throughout nature, and they have also very important pharmacological activity, anti-tumor, anti-cancer activity. All right, let's move on. That carbonyl group is a big deal in organic chemistry. There are quite a few functional groups under that general family, right? So what are they? As you can see, there's a split between aldehydes and ketones on the left and between carboxylic acid derivatives on the right. Aldehydes and ketones have the carbonyl bonded to either two carbon groups, two alkyl groups in the case of a ketone, or an alkyl and a hydrogen in the case of an aldehyde. Whereas carboxylic acid derivatives, a carboxylic acid is as indicated, and you know that already. We've seen a lot of carboxylic acids. When we look at acids and bases, we looked at a number of these. Acetic acid is a good example, a good example of a simple carboxylic acid. And so all of these carboxylic acid derivatives replace the hydroxyl that's bonded to the carbonyl with either an OR group in the case of an ester, or an NR2 group in the case of an amide, or a halogen in the case of an acid halide, or an O carbonyl in the case of an anhydride, right? Or even an O minus in the case of a metal carboxylate. So the carbonyl family is very extensive and very important in organic chemistry. Okay, then you have your nitrogen containing functional groups. This is a big family as well. And it's a very important family. A lot of natural products, a lot of compounds that are derived from plants, which are called alkaloids, contain nitrogen. In fact, the definition of an alkaloid is a natural product derived from a plant that contains nitrogen. A lot of these have very important medicinal properties. These include the amines, which is sp3 nitrogen bonded to 3 R groups, again, hydrogen or carbon alkyl, sp3 carbon. The imines, right, not amines, but the imines, which is carbon nitrogen double bond, as you can see there. The enamines, which is a carbon double bond with a amino group bonded to one of the alkene carbons. The amide group on the right, which is also listed under carboxylic acid derivatives. Completing this is a nitrile in the lower left, which is a carbon nitrogen triple bond, and finally a nitro group in the bottom middle, which is RNO2. Going back to the amide for a moment, that functional group, the amide, which is a carboxylic acid derivative, is one of the most important functional groups in biology. Can you think why? If you mentioned proteins and amino acids, you are absolutely correct, right? Proteins are comprised of what? They're comprised of 20 essential amino acids that are connected in a very special sequence. And the way they're connected is through the amide functional group. Now, biologists and biochemists refer to this as the peptide. You may know it as the peptide linkage, but a peptide is an amide. They're the same exact thing. And so it's a very important functional group in biology. So now we come to the end of our abbreviated listing of functional groups, the halogen containing functional groups, what you have here are the haloalkanes, I should say. That's on the left. That's sp3 carbon bonded to fluorine, chlorine, bromine, or iodine. And then you have your haloalkenes, and that's self-explanatory. Let me say that fluorine is special, right? Fluorine is almost in its own group. The carbon-fluorine bond is very strong. The carbon, chlorine, bromine, and iodine bonds are much weaker and much more reactive. Right, so you will see in your course where chlorine and bromine are used interchangeably. They have very similar reactivity, or bromine and iodine, but you're never going to see fluorine, right? Fluorine as an alternative to chlorine, bromine, or iodine, or almost never. All right, so that completes the mini-series, except to say one more thing. Going back a few lessons to reaction mechanism, if you remember, we said one of the main reasons that we put so much effort into reaction mechanism is twofold. Number one, that's the best way to learn organic chemistry, and that's how organic chemistry is organized. And then number two, we said, of course, if you want to optimize reactions, you need to know what's going on under the hood. So I should add to that. The way the way to learn organic chemistry and the way it's organized and the way your professor will present it and the way your textbook presents it, yes, is via reaction mechanism and functional group. Reaction mechanism and functional group. And this is a way to take a highly complicated field and make it a bit friendlier. All right. And this is what humans do. We organize things. We organize information. All right. So I hope you've enjoyed the mini-series. I will have one more concluding lecture lesson here to really cap this series off. And basically it's going to give you some recommendations and some tips when you actually begin to take organic chemistry, either from your professor or under my tutoring program, or a combination of the two, or some other arrangement. I want to give you the benefit again of many years of experience, seeing a lot of things that work and a lot of things that don't, in terms of what I saw my students doing and trying. And I want to give you the benefit of that experience so that you can have the best start you possibly can. All right. So anyway, hope you've enjoyed this, and I hope to hear from some of you whether you like this, why you liked it, how you think it could be improved, my presentation style. Does it work right simply with my voice or not? Do you really need to see me writing on a board? And anything else that you can think of. I really appreciate any of your comments. I just try to keep them constructive, okay, and appropriate. All right, take care. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.